When most of us think about STEM, we might think of doing things like studying the dynamics of stars, or designing college math courses, writing college textbooks, maybe running a science camp for kids, or teaching in an elementary classroom, or a middle school classroom, or a high school classroom. We might think about running professional development for science teachers. We might think about writing books for the general public about topics like climate change, astronomy, mathematics, statistics, relativity. We might think about writing children's books about science. We might think about developing science curriculum. We might think about giving talks to the public about science topics of the day, relativity or climate change or any of a wide range of other topics. What's remarkable about today's speaker is that he has done all of these. What's also remarkable about him is that he knew early on that he wanted to combine science and science education, and that he understood how important connecting the two actually is. The result is a long list of accomplishments in bridging both of those. Today he's going to talk with us about that connection, the race between education and catastrophe. Thank you.
Thank you very much. So thanks for coming. Just so I know who you all are. So I'm guessing that most of you are from the Graduate School of Education. Is there anyone who's not? Oh.
I do programs for teachers.
Okay. Who else? Chemistry.
I'm an undergrad.
In what?
Math.
Awesome. Awesome. Good. Cool. Thank you very much. So I've done talks on education for a long time, and I used to kind of do this talk that was kind of nuts and bolts that might help you in your teaching. And for a long time I was doing that talk and people asked me if I would write it up. And so I finally got around to writing it up. So it's all written up in this book. And then I decided that now it was written up in this book, I didn't have to give that talk anymore. And I could just give you all my fun examples that I like to talk about. So that's what I'm going to do instead. And you've got my email address there, so if you have questions or want to talk to me about anything that we don't get a chance to talk about today, please feel free to email me, jeff@bigkidscience.com. The title, The Race Between Education and Catastrophe, comes from my favorite quote, which is this right here from H.G. Wells, 100 years ago. Human history becomes more and more a race between education and catastrophe. And I think since most of you are involved in education in some way, it's probably pretty obvious why that would be my favorite quote as someone who focuses on education. And it's probably also why you're interested in it too, because we think this is really important, trying to get people to learn more about our world and how to understand what's going on and how to manage the power that we've acquired through science and technology. And I picked these three examples at the bottom just to give you a little taste of what I'm talking about. So the first one there, so I just picked this one selfishly to represent what happens when we're winning the race between education and catastrophe. We're using our power that we've developed for good things. So here you've got a Japanese astronaut on board the International Space Station reading a children's book about global warming and climate change and how we can solve the problem. It's selfish because I wrote the book. But it's a really fun kind of program, and it shows we are capable of kind of amazing things as a species, to have a thing up in space that many nations all work together on, and to have, you know, this kind of international diversity up there taking advantage of that. Then of course there's the other extreme of the race between education and catastrophe, which is fairly easy to understand that, you know, it's fairly easy to understand that this is bad. And yet we devote hundreds of billions of dollars around the globe every year to building things that can do that. And so you can see where this race starts to really come into play of how are we going to make sure that we focus and use our knowledge wisely and not unwisely. And then, of course, there's the third one here, which you probably recognize as the graph of rising carbon dioxide concentration. And this is maybe the trickier part of the race between education and catastrophe, because it doesn't take a lot to understand that this would be a bad thing for the human race. It takes a lot more to understand that this is a bad thing for the human race. And that's where the challenge of education becomes even greater. And with that, I'll give you my first brief advertisement. I'll have more for you later. But if you can come, I'll be talking about climate change tonight at a church there in Kensington and tomorrow night at the Lawrence Hall. So hopefully you can come out for one of those. So I thought what I would do in this talk is just give you a bunch of examples of how I view this race between education and catastrophe, and some of the things I like to do with kids, college students, the public. Depending on what subject area you're in, what you're teaching, you might be doing completely different examples, but hopefully they'll still give you kind of a sense of how you can get things across to them. And for me in particular, my PhD is in astronomy, astrophysics, so I'm very focused on what you might call a cosmic perspective. And in fact, what really got me on the path that I'm on was the original Cosmos series from Carl Sagan, which has been updated with Neil deGrasse Tyson. If you haven't watched them, I would highly recommend watching both, the original one and Neil deGrasse Tyson's updated version. They cover generally different things, so it won't be like just seeing the updated version of the old stuff. It'll be like seeing one set of things and then seeing a new set of things, and they're both really great. And to give you a sense of this, the first real big educational project I did was building scale models of the solar systems, and I started doing this with my elementary school kids that I was teaching. And then when I started teaching at the college level, I realized college students didn't have any better idea of scale of the universe than elementary school kids did, nor does the public. And in fact, one of the really interesting things about it was when we first built, this is our Colorado scale model, I'll tell you about it in a minute, but I'll just tell you the story first. When we first put it out there, we had professional astronomers, our colleagues, come and start walking through it, and as they looked at how tiny the planets were, this can't be right. And then they would do the calculations in their head, and they'd realize it was right, of course. And showing you that even people who study this for a living miss out sometimes on what the real scale of things is. So what we do is we build, there's this one at Colorado, then we have this one on the National Mall in Washington, D.C., a little easier to see the sun right there. So we've built the solar system on a scale of 1 to 10 billion. So everything's just divided by 10 billion to get the sizes. So the sun comes out, here about 14 centimeters in diameter, like a big grapefruit. So the first thing I'll ask you to do is what I always ask elementary kids to do, is show me how big the Earth is in comparison. So, yeah, it's small. Most people are pretty astounded by how small it is, because on this scale, the math is really pretty simple. Earth's diameter becomes 1 millimeter on this scale. So 1 millimeter is smaller than the ballpoint in your pen, if you have a pen. It's really, really tiny compared to that sun. When you see a photo of the sun with sunspots on it, those sunspots are enormous compared to the Earth. So you really get that sense of, gosh, our planet is really tiny. And then where is it? Well, it's in the little glass disk that's here, Mercury, Venus, Earth over here, 15-meter distance there. So you just get a little sense. So there's a lot of fun things that you can do with this model, but I'm just going to go to one, which is that you can walk, obviously, on this scale from the sun to Earth in just a few minutes, and hopefully by the time you get there, you're already going, wow, our planet's really tiny, and you start to understand a little bit of a cosmic perspective already that that's not a lot, and that's all we've got, and we better take care of it, right? But then you just keep going, and you can walk out. There's for the one in DC here, is the Air and Space Museum. Keep going out to Mars, and then cross the steps and keep going. And you get to Pluto, if you're familiar with the mall in DC, over by the Smithsonian Castle. So it's about 600 meters, roughly a third of a mile from the sun to Pluto. So you can walk it in a few minutes. So imagine you're in Washington, DC here, and you start walking, and in a few minutes you're over at the edge of our solar system. And then I ask you, okay, now how much farther do you have to go to get to the next star? Right, Alpha Centauri. And if you teach elementary kids, or even middle school kids, this is a really fun thing just to ask them to guess. Because when they start guessing, they'll usually guess, like half a mile. Somebody will say 10 miles, and then the rest of the class will laugh because that's so ridiculous. But, and for those of you, I know we got one math person here at least, it's fun to do this math, and one of the things I like about the 1 to 10 million scale is even elementary kids, 4th grade and up, can deal with it as long as you do it in metric. It's a disaster if you use English units, right? But in metric, you just got to drop off your zeros and convert your kilos and millis and stuff, right? So you take a light year, which you can calculate out how far a light year is, and it turns out to be right around 10 trillion kilometers. So on a scale of 1 to 10 billion, you divide 10 trillion by 10 billion, and that's 1,000. So a light year on this scale is 1,000 kilometers, and you can look up anywhere that the nearest star is 4.4 light years away. So that's 4,400 kilometers, 2,500-ish miles. It's the distance across the United States. So if you start here in Washington, D.C. at this sun, you got to walk to Berkeley to get to the next star. Kind of astonishing, right? Incidentally, another fun thing is you can ask, where's the moon? Right? The Earth is that little tiny ballpoint on the tip of my finger. On the moon, when the moon's 400,000 kilometers away, so on this scale that becomes 4 centimeters, which is about that much. So that's the distance from Earth to the moon on this scale. So think about that. On this scale, walking around out there, that's the farthest a human being has ever traveled. A robotic spacecraft have gone throughout the solar system, but a person has never gone farther than that. And to get to the nearest star, you'd have to cross the United States. So now you can talk about aliens, right? Because if aliens are coming to us from other stars, what's their technology like? Well, they have technology that, on this scale, is the equivalent of being able to cross back and forth across the United States, according to UFO reports, easily and often, sometimes just to pick up a farmer in Iowa. And that's the farthest a human being has ever gone. So you can see the technological difference between us and them. And we can talk more about that, but I'll save that for another time. You can think about it. And that was just to the nearest star. Remember, we live in our solar system. It's part of the Milky Way galaxy. You can't even see the nearest star on there because in that picture it's so close to us that they would overlap in the same dot. The Milky Way galaxy has something like 100 billion stars in it. Actually several hundred billion, but 100 billion's good enough. So again, just to think about that, I'll ask you the question I would ask the elementary school kids. So suppose tonight you're thinking about all this, you're having trouble sleeping because it was so mind-blowing, right? And so instead of counting sheep to try to get to sleep, you count stars. So you start 1, 2, 3. How long is it going to take you to get to 100 billion? Guess. So you're all shy, but that's okay. Kids like to guess. They will guess for you. But of course, you can calculate out an answer pretty easily if you make some assumptions. So if you assume you're counting at a rate of 1 per second, like I just was, it was 100, it'll be 100 billion seconds. Now, this is really fun to do if you ever get a chance to do this with elementary school kids, because they will, when you explain the 1 per second, they will immediately tell you, at least a few of them will, that they can count a lot faster than that, right? And they will demonstrate 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? And then you can just say, well, that's really good, but what about when you get to 48,992,346,851? Can you still say it that quick? And do you know what comes next? wherever you lost your place. So if you could actually keep going at 1 per second, that would be an impressive rate of counting. 100 billion seconds, you can figure that out. Kids can figure it out very easily. They will understand, 4th grade up, that they just get out their calculators, divide by 60 seconds a minute, 60 minutes an hour, 24 hours a day, 365 days a year, and you will see that 100 billion seconds is about 3,200 years. So think about that. Just to count the stars in our galaxy would take you more than 3,000 years. And that was just to count them. It wasn't to point a telescope at them to figure out which ones have planets in the right orbits to be Earth-like or might have life on them and so on. And based on our statistics from the missions that have been looking for planets around other stars now, we know that most of those 100 billion stars, and since there's really several 100 billion, at least 100 billion planetary systems in our galaxy, that would have a planet of close to Earth size in a close to Earth-like orbit. So this could also be that 100 billion, 3,000 years to count it, kind of the number of possible Earths that we have in our galaxy, possible places for life and civilization. And of course that's only our galaxy fades into the background of the universe. The universe also has like 100 billion galaxies in it. So 100 billion stars in each galaxy times 100 billion galaxies, if you do it in powers of 10, it's easy. 10 to the 11th times 10 to the 11th is 10 to the 22nd. So about 10 to the 22nd stars in our observable universe. So what's that number like? My son's at UCLA now, so he's bigger than that. It's a whole picture. But if you counted, like he gave up doing there, the grains of sand on the beach here in Waikiki where he was, counted every single grain of sand, and then kept going and counted every grain of sand on every beach in the entire world, the total result you'd get would be around that same 10 to the 22nd. So the number of stars in the observable universe, and again, remember, when I say number of stars, I might as well be saying number of possible Earths, is as many as there are grains of sand on all the beaches on Earth put together. So now you can ask, are there other civilizations out there besides us? Scientifically, we don't know. We don't have any evidence of them yet. But if there's not, it's like out of all the grains of sand on all the beaches put together, there's just one grain, us, that's different from all the others. Almost becomes impossible to believe at that point, right? So you kind of get that sense. Well, why do I tell you all this? You know, I'm going quickly through some fun examples, but there's an important lesson here that relates back to the difference between education and catastrophe. And the important lesson can be summarized very simply. We're not the center of the universe. Now, if you think about human history, that's kind of a radical idea. Because for most of human history, it was assumed that Earth, and maybe by extension us, were the center of the universe. You might argue that some of our behavioral patterns developed based on the assumption that we are the center of the universe. But now we find out we're not. And I would argue that if you look at most of our problems around the world, whether they're big problems caused by, you know, some powerful person, or small problems, interpersonal problems that you might run into when two people get upset at each other, I'd say I think most, if not all of those cases, you can trace it to not getting that, what I call center of the universe syndrome. So people behaving as though they believe the universe revolves around them. And again, I think if you think about that, you'll get that sense, you know. Kim Jong-un, whatever, he thinks the universe revolves around him. He can do whatever he wants. When two people are in an argument, usually it's because someone's not willing to look at the other person's point of view because they think they're more important than the other person, because they're the center of the universe. I think if we all recognized that we're not, and really understood that, everybody would treat each other better. Pay no attention to the date there that I posted it. I actually had that in a book from 10 years earlier, but felt like I needed to post it again for some reason. Now, I said I wasn't going to do much of nuts and bolts teaching, but I'll give you a couple things that try to tie together a little bit of what I was talking about back to what you can do directly. And I think why I like that example, even though you can do the same with any subject and anything you're teaching, is because it gives you a sense of, I think, there are three things that have to be done all together for any teaching at any level to be successful. And the first, so I'm going to call them education, perspective, and inspiration. I have to define them because I'm not necessarily using them the way you'd always think about it. In this case, by education, I mean your concepts and content that you're trying to deliver to your audience, whoever that is. So if you're teaching a class, if you're teaching chemistry, for example, you've got a certain set of material that those students need to know in order to pass your test and move on to the next course. That's the education piece. What I would argue is one of the fundamental problems we have in education, particularly science education, is that that's where we stop. And if you stop there, you say, here's what you need to know. Sort of a natural human reaction would be, why? Why do I need to know that, other than that you're going to test me on it? Why should I care about what you're going to test me on, what you're telling me I need to know? So the other two pieces are designed to try to make the case for why your students should actually learn the content that you're delivering. And I would say that perspective is what makes something interesting. So when I'm giving you those cosmic perspective examples that we just did, the reason, if you do remember them later, the reason you're going to remember them is because they made you think about us and our planet in a different way once you realize the scale and how big the universe is and so on. It shifted your perspective. And whenever your perspective shifts, that's interesting and it's fun to learn. So your task in whenever you're teaching something else is figure out what the perspective shift that you want your students to have is and make sure they get it. Even if you have to tell them explicitly, here's how your thinking should change, and help them pick that up. And I think that applies to anything, even just to take sort of a minimalist example. If you're taking a foreign language course and you learn a new word, it's like, cool, now I can say that in this language that I couldn't. That's a new perspective for you that you didn't have before. That's why it's fun to learn. And then we don't want just learning it right now to be the end of it. We want it to inspire our students to keep going beyond that. And that doesn't, if you're teaching a chemistry class, it doesn't necessarily mean that they're going to go on and become professional chemists. It just means that whatever they learned should in some way inspire them. Even if there's a particular fact or concept that they might not use again, it should be taught in a way that inspires them to think, I get why that's important and how it affects us as human beings. So if you put all three things together, you're going to be more likely to succeed in your teaching than if you just try to deliver content without helping people understand this. And the main reason I point this out is because I think, particularly at the college level, people underestimate how important it is to be very direct about that. I think a lot of people, when you're teaching something, you just assume, well, for me it's really cool, so it's obviously going to be cool to my students too. But that's not necessarily obvious to them. You have to tell them why it's cool and interesting and shifts perspective and is inspiring. Otherwise, they may not figure it out on their own, and then they'll wonder why you're teaching it to them. Whereas if you make it clear and explicit, you'll succeed. And I'll give you just an example from one of my children's books. I always try in everything I'm working on, whether it's college textbook or kids book or public, to try to mix all three things together as much as I can. You can't always do all three on every page of something or in every lecture that you give, but you can try your best. And here, this is from my book, Max Goes to Jupiter. Max is the dog there. And so they're approaching Jupiter, So it says, as the ship approached Jupiter, the crew fired the rocket engines, slowing their speed until Jupiter's gravity could hold them in orbit. They stared out the windows in awe as they orbited around Jupiter for the first time. Captain Anusha was the first to notice Earth in the distance. She couldn't help but marvel at the sight, especially as she thought about the different nationalities of all the crew members. It sure makes you think, she said. We all come from countries that used to fight each other. Now we are all working together here in a tiny ship from which our whole planet looks barely as large as a mote of dust. And that's Earth right there. And so you can see there's a lot of educational content, why do they have to fire engines to slow down and enter orbit and so on. But I'm not being subtle about the perspective shift or the inspiration parts either. They're very, very direct to make sure the kids don't miss out on it. And incidentally, the mote of dust reference is from Carl Sagan, from what he used. And that's actually explained over on the side of the page there. I've done a lot of teaching, not only of science, but also of math, and in particular what we call quantitative reasoning. So it's kind of math for the everyday life things. It's what, at Colorado, this is what we require our students to take if they're not going on in science or math in a STEM field. And I just want to give you a few examples of this because they're fun, and it again, I think, illustrates a little bit about this race between education and catastrophe and the kinds of things that people need to know that we're not necessarily teaching them at the moment and need to do a better job of. But first, I have a multiple choice question for you. I'll put up the choices as we go along. So you've just struck up a conversation with a dynamic, successful whoever. You can pick who it is that you're talking to. Which of the following are you most likely to hear during the course of your conversation? The other person say. A, I really don't know how to read very well. B, I can't write a grammatically correct sentence. C, I'm awful at dealing with people. Remember, this is a dynamic, successful person, right? D, I've never been able to think logically. Or E, I'm bad at math. Think about that, right? You know the answer, right, is obviously E. But think about what it means as a society that someone who is dynamic and successful would actually say this out loud. You would never hear them say any of those other four things. And yet we've got a lot of people saying that. And I would say that's a big problem. Because, for example, one of the sad statistics that has been collected on this is that the profession most likely to say that is elementary school teacher. What happens to a kid when they hear their elementary school teacher say that? Well, most kids love their elementary school teachers. So they hear somebody that they love and respect saying it's okay to be bad at math. What's the message it sends them? It's okay for you to be mad at math, too. So it spreads like a social disease from one person who says it to the next. So the first thing, particularly when I'm talking to elementary school teachers, that I would always tell them is even if you believe this is true, don't ever say it. If you hear somebody say this, even in casual conversation, try to call them out and talk about why that's really not a great thing to say. Secondly, it's in almost all cases not even true, right? Take an elementary school teacher, for example. They graduated from college. They can't be that bad at math or they wouldn't have gotten through it, right? So it's usually not even true, and yet they're saying. Thinking big, I don't have time because I want to go get to some discussion to go through a lot of these things, but I'll just very briefly, the athlete who earns $1 million a year, how long does it take to earn $1 billion? The math is simple. It takes 1,000 years. But that blows people's minds, right? Because million, billion, trillion all sound the same except for the first letters. To realize that there's this factor of 1,000 between them takes thought. So you have to pull up what kind of examples can I give. And then what's your share of the $23 trillion? It might be $23 trillion by now. So there's a nice little rule of thumb that you can do just by taking 1 trillion and dividing by the population of the United States. So $1 trillion is $3,000 per person in the United States, approximately. So your personal share of the $22 trillion debt is 22 times that, or $66,000. Family of four, you know, we're up close to $300,000 is your share, your family's share of the debt. For most people, that's larger than any other debt you will have, including mortgages, college loans, everything else. But we don't even think about it. Now, you can have arguments about how bad deficits are, and that's a separate thing for economists. But you can't have that argument if you don't understand what it means. If it's just a number, right? You have to have some way of putting that number in context and perspective in order to have a thoughtful and intelligent opinion about it. Statistics is all over everything we do. It's very important for people to understand statistics. And as you probably noticed from the news, most people don't understand much about probability and statistics. I just want to give you a couple of little examples here of this visual one, because it kind of illustrates the problem we have without getting too much into the solutions at the moment. But this is just changing value of the dollar. I picked it because it's the kind of graphic you might see in the news, on TV, or in a newspaper almost any day, right? So this is showing 1980 $1, 2016 34 cents, and this length here is 34%, you know, 1/3 of that. So this is actually a legitimate graphic. I mean, it's not lying to you. This is 1/3 the length of that. But what does your brain do when it sees it? How does your eye and your brain focus on this? You're looking at the size, the whole size, the area, right? And the area of this one, you know, since it's 1/3 in the length, it's 1/3 squared, or 1/9 of the area of this. So perceptually, you see this as way smaller than the actual difference is. It's a very well-known perceptual distortion. And yet you see this in the news all the time. Like I said, it's not wrong, they're not lying to you, but if you don't know about how the perception works compared to, you know, the length, then you will be misled by it. And this is a relatively minor example, but you can probably think of examples where this kind of perceptual trick causes a lot more problems for people. And then I just want to show you one other. This is a graph of changes in college tuition from the early 2000s till just a couple of years ago. And if you look at this graph and you don't look at this axis here, then you would be looking at it the way I would argue that most Americans do. And if you, or even most college students probably do, and you would look at that and you would say, I'm really glad I didn't go to college back when it was really expensive, since it's gotten cheaper, right? But of course that's not what's going on at all, because if you read what it says over here, this is the percentage change from the previous year that's being graphed here. So this is a graph of the rate of change. So now you can ask yourself, when do we teach students how to interpret a graph of rates of change? What's the answer? You know, right? Rates of change is a topic from calculus, right? So you learn about this in calculus. Except for most Americans and even most college students never take calculus. And yet you see graphs like this all the time. Do you actually need calculus to understand this graph? No. But we don't ever teach them this kind of thinking. And then they're going to be misled, because here's what's actually happening to college costs there on the right. And I got one more sort of statistics probability example for you. It's your best strategy for getting an extra $1 million. It's, again, a multiple choice question. A is to buy a lot of lottery tickets when the prize is big. I haven't shown you the rest of the choices yet. Based on behavior, that is the choice that most Americans would pick. Because about half of Americans play the lottery, and per capita lottery spending among that half is around $500 per year. So you have people who earn $20,000 or less per year spending $500 of that on lottery tickets. because it seems good if you don't understand the probabilities and what they mean, and we haven't taught them that. B, become a professional athlete. You know, it's easy when you're a high school or college athlete to see the salaries that professional athletes are getting and think, hey, I'm pretty good, I'm going to get that. But then you realize it's like still, even at the college level, less than 1 in 1,000 that will end up getting a contract. Go to college, invest in the stock market, get a restaurant job. I'm just going to quickly give you the answer, which is C. That's the median salary for a high school graduate. This is about 3 years old, this data here, $36,000. Median salary for a college graduate, $64,000. So that's a difference of $28,000 per year. Assume you work 40 years from age 25 to 65, and that's $1.1 million bonus on average, on median, for going to college. That's kind of impressive, right? Obviously, it depends on if you're a STEM major or you get better grades, you're more likely to be at that median or higher than someone who's not, but there's certain amounts of luck involved and so on too. But still, on average, going to college is going to get people an extra $1 million over the course of their lifetime. There's not really a better investment that you can make. And the last little example, because I told you this stuff is important, the bad at math disease has consequences beyond the individual stuff we've been talking about. This is just a graph of median home price to median household income. So take like 3 on the vertical axis there, for example. Imagine you earn $50,000 a year. 3 means you bought a house that's 3 times that, so a $150,000 house. And what you see is that historically it was generally around 3-ish, but then in the early 2000s it shot up to almost 5. So what happened? All of a sudden, somebody who earned $50,000 a year was buying a $250,000 house instead of a $150,000 house. So now you ask yourself, how's that possible? And you can spend some time thinking about how it might be possible, and you'll come to the conclusion that it's not. It's not possible. So this was obviously a bubble that was going to burst, and when it did, it caused the Great Recession. How many of you have seen the movie The Big Short? Okay, great. If you haven't seen it, I highly recommend it because it goes through all this. This is not something that you can only see in hindsight. The data were all there in advance. And nevertheless, you had these banks pretending that these loans were all good. You had loan officers telling you, yes, you can afford way more than you thought you could. And then you had you believing them. And it led to the recession. So what caused the recession? Bad at math disease. So again, if we weren't so afraid as a nation to look at the math, I would argue we could avoid problems like this. The last main example I'm going to do for you is the parable of the bacteria in the bottle that comes from a professor at Colorado, a physics professor who passed away a few years ago, Al Bartlett, kind of an amazing guy. And here's this problem that he set up. At 11 o'clock, you place a single bacterium in a nutrient-filled bottle. So it grows, eats the nutrients, grows, divides into 2 at 11:01, eats some more, grows, divides into 4 at 11:02, 8 at 11:03, and so on. So it's a very simple setup that you've got a doubling time of 1 minute. That's faster than real bacteria generally grow, but makes them simple to think about. Rather than having you do a bunch of calculations, what Dr. Bartlett said was, here's your scenario, that at 12 o'clock, the bottle is full and the nutrients are all gone, and therefore the bacteria all die. So in thinking about the race between education and catastrophe, this is a bacterial civilization that lost the race. They have a catastrophe at their end. They all die. So it's a very sad story. But now, following what Dr. Bartlett used to do, with a few slight modifications, I'm going to ask you some questions about this. So you all got the scenario, 11 o'clock, we start with 1 bacterium, they double every minute, 12 o'clock the bottle's full. So question number 1 is, when was the bottle half full? What's the answer? A minute before, 11:59, right? Because they're doubling every minute. What do you think most students and most Americans answer? 11:30, right? Most pick 11:30, halfway there. But But yeah, it's 11:59. And once you explain that to people, at first they're like, huh? But then when you explain the dumb one, they go, oh yeah, that makes sense, I get it. Okay, so question number 2. You are a mathematically sophisticated bacterium. At 11:56, you recognize the impending disaster. You immediately jump on your soapbox and warn that unless your fellow bacteria slow their growth dramatically, the end is just 4 minutes away. The question is, will any of them believe you? So notice the question is not, are you correct? You are correct. Right? The question is, will they believe you? So now think about it from sort of the average bacterium or average American's point of view. Not saying those are equivalent. Right, 11:59, the bottle's half full. So 11:58, it was a quarter full. At 11:57, it was an eighth full. And at 11:56, it's a 16th full when you're on your soapbox. So you're on your soapbox telling them the end is 4 minutes away. What do they see? It's already been 56 minutes. 1/16 is used up, 15/16 are untouched. There's 15 times as much untouched nutrients as you've used in the whole first 56 minutes. That makes no sense that you can have the end be 4 minutes away, so no, they don't believe you. Question 3, just before the disaster strikes, they go, oh my gosh, that guy was right, that woman was right. And so they start a bacterial space program to try and see if there's any hope for them. And they discover that there's 3 extra bottles full of nutrients out in the lab with no one living in them. So quick, they start a bacterial population redistribution program so that they disperse their population from the 1 bottle into now what they have of 4 bottles. So how much more time does that buy them? So to me, one of the amazing things about this, because I've done this many, many times with students, public, and other, is that even after you've helped them, and we went quickly, but even after you've helped them understand why it was 11:59, why you're correct at 11:56, and they get it, because it's not that hard to understand. When they see this, the typical reaction is they know it's not right, but they really want to save 3 more hours for the 3 more bottles. And of course, 1 bottle after 12 o'clock, 2 bottles at 12:01, 4 bottles at 12:02. And then the last question is there any hope that future discoveries will allow the colony to continue its exponential growth indefinitely? And the answer is no. If you want to calculate, it's kind of fun. You know, you can take, for example, make the assumption, which is pretty accurate, that a typical bacterium is a cubic micrometer in size. And incidentally, if you do a cubic micrometer, then after 1 hour, there's 2 to the 60th bacteria in the bottle, and 2 to the 60th cubic micrometers is actually about the size of a bottle in the lab, so it's pretty good. At the end of the 2nd hour, they'd be covering the entire surface of the Earth 2.5 meters deep. And there's nothing to, you know, that's kind of unrealistic to begin with that they could ever do that. But there's nothing to stop you from calculating further. And if you do, you'll find that after 5.5 hours, your calculated volume of bacteria would exceed the volume of the observable universe, 14 billion light years in radius from Earth, you know, which obviously can't happen because there's nothing to eat once they get out into space. And to go 14 billion light years in 5.5 hours would violate relativity. You can't do that either. So the answer to that question is no, it's not possible. It's not an opinion-based question. It's just not possible. And going back to the race between education and catastrophe, you know, these bacteria lost their race, and you can see what's going on there, right? This is the graph, and the reason it catches you sort of in a way that's hard for your mind to grasp is because it all kind of happens really suddenly, seemingly, in the last few minutes. And this is not the same graph, even though it looks very similar, right? This is a graph of human population over the last 12,000 years. So you look at that and you say, well, what's the lesson here? The lesson here is that you can ask the same question. Can our population continue to grow like this? And the answer is no. That's not an opinion. It's not a political opinion. It's not a belief. It's just a fact of nature. This cannot continue indefinitely. Now, it doesn't tell you how much further it might go, right? We could have debates, political, theological, whatever, about how much further it might be able to go, but indefinitely is not an option. And once you recognize that, that will shape the kind of discussion you have about this. But if you don't recognize that, and you think this can just keep going, then you're headed towards catastrophe. So for the last thing that I want to do with you here, just so I give you a couple more nuts and bolts takeaways, I want to tell you the one key to student success. And this applies to everything: college, elementary school, grad school, whatever. And I like to put this slide up like that because nobody ever believes that I have one key to student success. I mean, how can there be just one key to student success? But I'm going to show it to you, and you're going to agree with me. Right? Learning requires study and effort. But think about this, particularly if you've had experience with elementary school kids. Ask elementary school kids or their parents, how do you get to be good at soccer? And they will tell you they have to put in a lot of practice and effort. Ask them, how do you get to be good at violin? And they'll tell you, you have to put in a lot of practice and effort. Ask them, how do you get to be good at math? Oh, I just sit there in class and listen to what the teacher says. For some reason, people haven't recognized that learning math or science or English or anything else requires the same kind of study and effort that musical instruments or sports do. We need to make sure that our students understand this and help them to succeed. So you got to make sure when you're teaching, the single most important thing you can do to help your students succeed in your class is make sure they work. You know, give them enough homework so that they're putting in the time, putting in the effort. Make sure it's interesting so it doesn't feel boring and tedious, that it has the perspective and the inspiration associated with it, so that when they get done with it, they're like, I'm actually glad I did that, even though it took a lot of my time. But that's what it takes. I actually have a handout on this. If you're teaching college, you can download from my website, How to Succeed in College Classes, that goes through how they can put in some study and effort. It's just a front and back. You can hand it out in class, or they can read it online, PDF. And I'll just put in a plug for the book. If you want more nuts and bolts, it's got a list of strategies and things that you can talk about. And then before I turn it over to questions and discussion, I just have a few more little fun things I want to show you that I've been working on and involved with. The first is, and you can do this now, get out your phone and download this app that we created, Totality Like Big Kid Science. It's free, and it shows you where you need to go to see the next eclipse, total eclipse, and has a bunch of other information available. And the next one, as there was one this summer down in Chile and Argentina, and coincidentally the next one, December of next year, is also in Chile and Argentina. So if you know people down there, it comes up on their phones in Spanish automatically, so tell them to. It's all free. Told you about this a little bit in the beginning.
Hi, I'm NASA astronaut Mike Hopkins on board the International Space Station, and it's one of my favorite times. It's story time from space. Now today's story is Max Goes to the Moon, a science adventure with Max the dog.
So you go to storytimefromspace.com, teachers can stream it right into their classroom, watch the astronauts reading books from space. Read about 20 different books from space, including all 6 of my kids' books at this point. So it's a lot of fun, another free resource for teachers. And then I'll just tell you the one thing that, if any of you are involved with middle school right now, I could use your help, because I'm working on a middle school project. It's at grade8science.com. You can see the sample chapters that are up there. If you know middle school teachers, please encourage them to take a look and try it with their middle school kids if they're teaching Earth and Space Science, usually done in 8th grade. And then email me with feedback so we know whether it's worth continuing or how to make it better. I mentioned my talk tonight at the church, tomorrow night, 6 p.m. at the Lawrence Hall. There's a reception at 5:30. Technically, you're supposed to register on their website. It's free, but they wanted to make sure they didn't fill up that much, but I don't think they will, so I wouldn't worry about it too much. Those are my 6 books for kids, the books for the public, my college textbooks, and thank you. Now we can take questions, discussion about these various ideas to help all of you win the race between education and catastrophe.
have a question for you. So I'm no longer a teacher, but when I did teach, I taught high school history and social studies. And I'm curious about what you think about the intersection between those. College campuses are much more siloed even than high schools are. And so I confess that as you were going through your slides, I was looking at them from the perspective of, history, sociology, et cetera. And the approach is very different. Like, for example, the rate of change, I'm like, well, you teach that in economics. Like, that's not actually something you don't do without calculus. Like, so I guess I'm curious about where you see ideal intersections between disciplines where other disciplines have something to bring to the table to complement what science is doing and what math is doing, because
and vice versa, yeah.
Yes, vice versa, but I'm pushing it that direction partly because as a person who deals with the history, social sciences a lot, and the humanities, there's a great deal of pressure in favor of STEM, and I guess I'm trying to push back and say I think there's as much benefit to be had the opposite direction as well, and I'm curious about where you see those intersections both ways.
Yeah, I mean, I think that's a very important point, and I'm a big believer in what's been called liberal arts education, right? The tradition that you take everything and learn about everything regardless of what your specialization area is, because that's critical. To just take this race between education and catastrophe, even with the examples I'm giving you, how are you going to understand why that's this race if you don't know history and what's happened in the past as a result of people? War has always been technology-based. History's always been technology-based, and so on. So you have to do both things in order to follow. And I would say in terms of the strategies, the same ideas apply. I think when you're teaching history, the good teachers connect to your perspective and your inspiration, and that's why it's really interesting. And the poor ones just tell you, here's the facts to memorize, without that context. So. And the other thing you can look at from that, I showed you that $1 million bonus for going to college, and I mentioned that STEM majors and better grades tend to be above average, and those are two independent things. So a history major who's getting good grades is likely to be above that median because there's lots of data on this. Liberal arts degrees do get you good jobs if you've done well. So, does that kind of answer?
Yeah, I just was curious what you think.
Yeah.
So to pick up connections with other disciplines as well, economics is built to a large extent on the notion of indefinite growth. It seems like a heavy lift to convince economists that can't go on forever.
I think economists have really come around on that. There's a lot of work that's been done, a few Nobel Prizes given out on topics related to that. So I'm not sure that that's so much the case anymore. And and I was going to mention on your point about the silos and the economists and the rate of change. I used to, sometimes I had groups that were really mixed with people from the economic side and people from math and science, and I just say, now when I say derivatives, you all know what I'm talking about, right? And then I'd ask the room what they thought I was talking about, and it was half the room thought I was talking about rates of change, and the other thought I was talking about stocks. And so you get that sense of, yeah, we do really silo. One of the things you might have seen on my list of strategies is get rid of the jargon, because different disciplines use the same terms in different ways, and so just speak in terms that make sense instead of always having to have a jargon term for everything.
I'm sorry.
Yeah.
It's just the slide that was most striking to me from a history standpoint versus a science or math one was the one about population growth, because Malthusian thinking has like a very clear historical arc. It has lots and lots of different historical effects in the world, and no one in the stuff that I'm reading on that sort of realm of the world predicts infinite growth or exponential growth in human population to continue.
Mm-hmm.
And so what I thought was really interesting about that slide is, like, I liked the examples. I thought it was really helpful thinking about the bottles growing. But what was interesting to me was, it was based upon a presumption that would never arise in certain disciplines, because the concept of when population growth begins to slow and what economic and social and political factors would ever cause that to happen, and whether, like, that's
Right.
a whole portion, like, that's a whole study
Yes.
in one realm. And then this, like, mathematically, sure, it's possible, but my mind was like, yeah, but blah, 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 like, there are all these reasons why of course that wouldn't happen. And so I thought it was an interesting difference in perspective and, like, how one would approach it. Like, you're saying it's mathematically impossible, and I was thinking of all the reasons why it wouldn't happen anyway.
Right. So when we're actually teaching this in like my quantitative reasoning course in the book,
Yeah.
we do talk about all those things. You know, I just gave you the little.
Yeah, no, and I wasn't assuming
And-
that you thought
but
it
I
was
think
going to happen.
the
I just-
part that I found that I think, you know, I think that a lot of people in the social sciences, what I found, overestimate what their students
Oh, yeah.
and the public might be thinking. I think the students and the public are thinking that can continue indefinitely. You, because you've been studying it for a long time, know, well, of course, you know. But you have to get that conversation started. Okay, wait, that can't happen, so what could happen? And here's something more realistic, and here's why the, you know, Malthus didn't, his predictions didn't come true. Here's all the negative ramifications of people who took that too seriously that have happened in history, right, and so on. Eugenics and all that kind of stuff. You can talk about all those things, but you know, the point I usually try to make with that is there's clearly a perfect answer to that, which is to just level out smoothly. But that won't happen by magic. It happens because people make conscious decisions to have fewer children on average. Otherwise, it has to happen either by deaths increasing or by births decreasing. We get to choose. The bacteria didn't. And so, you know, that framing is something that I've found most people don't get until you hit them with that first
No,
example.
I thought that was a really interesting one, because you have to have math to understand it, but you have to have something else to talk about why it's meaningful, and I thought
Yeah.
that was an interesting
Yeah.
conversation.
Thank you very much.